We now look at some battery electric vehicle type applications. Now, of course, there are other battery pack applications that are similar to these, and maybe they're not vehicle scenarios. But here I'm just using a vehicle to motivate the discussion. Battery electric vehicle battery packs are used in slightly different ways from just regular hybrid electric vehicle battery packs. The battery total capacity is larger because I have to be able to drive some distance. The relative rate of energy usage is lower. The range of state of charge used by the vehicle is larger. And one key point is that a plug-in or a battery electric vehicle is sometimes fully charged to a known set point. And we can take advantage of that, and that can be really helpful. In the simulation, we're considering a battery pack with a total capacity of 100 amp hours. That may be a little bit on the low side, but it's within the range. And a maximum rate on the current sensor of plus minus 5 q-nom, which for a battery electric vehicle is probably pretty good. For a plug-in, it may be a little bit on the low side. But these are values that you can play with, of course. In the simulation, we're going to once again assume a 10-bit current sensor, which gives us a quantum. This is 2 times q-nom, because, 2 times, there's a missing q-nom in there. It should be 10 times q-nom is what that is. And the sigma yi squared is computed in the same way as it was before. It's the q squared, which is this, times number of measurements divided by 12. Just the q squared over 12 is the variance of one measurement, and the 3600 is the conversion between ampere seconds and ampere hours. We'll look at 3 electric vehicle scenarios. And in the first one, we assume that the total capacity estimate is updated on a regular basis as the vehicle operates. And in this case, the number of measurements between updates is 7,200 seconds, or 2 hours. Now, not everybody drives 2 hours all the time, so you could argue that, hey, this is only ever going to be updated on long road trips, and so you'd be right. This would probably not be a very realistic scenario, but we'll do the second scenario we do is probably much more realistic, and we'll look at a different way then. So 2 hours, we could say maybe that would be roughly 120 miles if we're doing some kind of a road trip, maybe a little more, maybe a little less. And assuming a battery pack that can do, about 300-mile range, then that would change the state of charge by about plus minus 40% in that interval. So we're going to say that the true value of xi is chosen to be a uniform random variable between minus 0.4 and plus 0.4. And we'll assume a pretty good SOC estimation error, so the variance of the difference in states of charge is going to be 2 times 1% squared. The recursive methods are initialized with a total capacity estimate of 99 ampere hours, where we said the true capacity was 100 ampere hours. Here are some plots. By now you've learned to read these plots, so they should be able to look at them and pretty quickly glean some important information. First, the weighted least squares, if I zoom in once again, has really, really tight error bounds, and even though the estimate doesn't look awful, it looks pretty close to the truth of 100 ampere hours, the error bounds are not reliable, and the data shows the goodness of fit to be very bad. So we throw out that method. We do not use ordinary least squares methods, even weighted ones. Looking at the weighted total least squares method, remember that's non-recursive, uses all the data available at every point, and I can't initialize it. So it's a little bit bad at the beginning because of the inability to initialize the algorithm. Its error bounds are a little bit bigger than some of the others, perhaps, but eventually these 3 methods converge to the same basic neighborhood of each other. And so you can see the error bounds are always encompassing the truth for the weighted total least squares, and approximate weighted total least squares method. All of those give perfectly acceptable capacity estimates. And notice that the error is about 0.5 over 100, which is a very small value percentage-wise. The goodness of fit, the last three methods, all just about exactly the same, all very good. So for this scenario, again, ordinary weighted total least squares, bad, don't use it. Any of the other three methods, good in principle. Weighted total least squares is hard to implement. Remember, it's this non-recursive method, so we probably don't use that. But any of these two methods seem to give good results in this case. The second scenario is probably more realistic for a plug-in hybrid or electric vehicle. In this case, we are going to drive a random distance. Rather than updating every 70 to 100 seconds or 300 seconds or some number of seconds. We're going to take into consideration the entire drive cycle when we are updating our capacity. And the reason for this is the quality of our total capacity estimates is really limited by the noise on our SOC estimation error. So if this noise can somehow be reduced, then the total capacity estimates can become much more accurate. And the BEV application lets me do this. So I go out, I drive for a while, and when I'm done driving, the SOC is at some point, and then I charge the battery. So the charging is nice and controlled. It comes up and tapers off, and by the end, I have a calibrated SOC point. So let's say that we assume we know that point exactly, but this point, the SOC, has error bounds on it. So in terms of Z1 or Z2, I know one of them. And I could even do 2 updates per drive cycle. I could say that I've previously charged, and I know this point exactly, so at the bottom of the drive cycle, I have some error. And so I can compute using 0% error here and maybe 1% error there. It would probably be cheating and unrealistic to say I could get away with 0% in both, so I discharge and charge. That's probably being a little bit too optimistic. But here, let's say we assume we know one of the measurements perfectly, but not the other one. So sigma z is cut in half. Or sigma xi, rather, is cut in half. Well, that's a big deal. Now, the trade-off is that we don't have regular updates any longer. It's not every 300 seconds or 7,200 seconds or whatever number of seconds. The updates happen after random periods of time, just whenever the vehicle is charged. So mi becomes a random variable. And we need to model this in order to do a simulation. And there's a million ways to model this. The one I've chosen is just a way, and there's probably not motivated by anything terribly real. I just thought the curve looked reasonable to me. And I chose this curve as a PDF of the length of a drive cycle for an EV type scenario in hours. So the mode, the maximum probability, is 0.5 hours. So you can say, well, how long does it take me to drive to work or to other places? And for me, my drive to work is a little bit shorter than that. But if you lived in a really populous area like the Bay Area of California and you commuted to work, it's probably much more than that. So this is going to vary from person to person. So I just chose a person whose regular drive was more or less a half an hour, but who once in a while went on a longer trip, up to more than 3 hours. I cut it off at 3 hours because the probability of more than 3 hours is kind of vanishingly small. This is a log normal random variable. There's nothing special about it. I just chose it because it seemed reasonable to have quite a bit of probability with short drive cycles, going to the store, going to this, going to that, going to work, but then some probability of a longer drive cycle on occasion. Is it real? I don't know. Someone would have to do a study. It might be more like this would be real, but whatever. You put your own PDF into the simulation and try it out and see what it does. Again, I urge you to please experiment with the code that I give you. That's why I give it to you. Since a greater fraction of the battery pack is used for an entire drive cycle than for a regular periodic update, I'm using an 80% range of SOC. Again, change that if you think it's not the right number. And I'm computing a value to be uniform between minus 0.8 and 0.8 in the updates. Here are the results of the scenarios. Again, the blue line, the weighted total least squares, gives an appearance of working, but again, we have the error bound problem. The error bounds are just too tight, and if you look at, you can kind of see it there, that the goodness of fit is essentially 0, and that method is discarded. The weighted total least squares method works fine, except that it's not recursive, so it's not very helpful. The total least squares method is maybe the biggest surprise, but once you think about it a little bit, you realize why. That's the red line with the red error bars, and you can see, okay, there's maybe a little bit of a blip there where the error bars are not good, but over most of the scenario, it seems to give really good results and really good error bars. However, look at this. The goodness of fit for total least squares is pretty bad. And you ask yourself, well, why is that? Remember, for total least squares, we said that the sigma xi is equal to a constant times sigma yi. And if the sigma xi, this is the delta SOC, if that's constant, then the way to enforce this is to make sigma yi constant also. And one way of doing that is having the same number of measurements. So if mi is always the same, then sigma yi is always going to be the same, and the total least squares method is going to work. But in this scenario, we've got random mi. We've got random intervals of time that elapse between charging, and therefore the total least squares assumption is not met. And the total least squares method fails. Now, the estimates look good, but the estimates can't be trusted according to this result here. The approximate weighted total least squares method, however, does give a goodness of fit. That works very well, and it approximates super well this weighted total least squares, but it's computable and so forth. So in this case, in terms of accuracy and goodness of fit, these are the only two methods to choose. And in terms of computability, the bottom one, the approximate weighted total least squares, is really the only possible choice for an application like this, for it to be robust and accurate with any kind of a guarantee. The third scenario that we looked at is identical to the second scenario, except that we simulated a changing total capacity. And so 1,000 drive cycles, that might be 3 years. We're saying the capacity goes from 100 down to 90, so we lose 10% in 3 years. If it's completely linear, 30% in 9 years, about. That's pretty fast. We wouldn't expect a real battery pack to age that quickly, although it's within the realm of reason. So if we can track this, we should be able to track anything realistic, is the point. So the slope is minus 0.1 amp hours per measurement update, and here I use a forgetting factor of 0.98 in the algorithm. Look at the results. All of them give estimates that look quite good. The weighted least squares estimate, however, again has the same problem with error bounds, and the goodness of fit comes back saying, sorry, please don't use me. Surprisingly, maybe because we still have the random update interval, the total least squares method, it starts out saying, I'm not real sure about this, but eventually it actually does work. And I don't have any great explanation for that. It's just what the goodness of fit method says. So it says, at least in this case, didn't work for a while, then it worked. So after a point in time, you can trust it. Well, what about before that time? That's a bit of a problem. The only one that is computable and gives you goodness of fit that's acceptable for all points in time is, again, this approximate weighted total least squares solution. And it very robustly works all the time, gives you a decent goodness of fit, it gives you good error bounds, gives you a good estimate always, and it tracks a moving capacity. So there's nothing to complain about. So that's the end of these scenarios. I'm going to stop this section right now, and the very final section summarizes some of these results that we've already gone over. So we'll go through that pretty quickly, and that will be the end of this chapter.